This is the second part of our discussion on the concept of series. So far, we have defined what is an infinite series, when does it converges, and when does it diverges. And we have also discussed the relation between series of complex numbers with the series of real numbers. So, in fact, given a series of complex numbers, there are two related series of real numbers. So, one corresponding to the real parts and one corresponding to the imaginary parts. Now, in this discussion, we are going to explore some operations on infinite series. So, for example, if given two series, how to add them and how to multiply them. So, in this discussion, we will focus on the Cauchy's product of series. Now, one condition that we are going to impose in this discussion is that the series has to be convergent. So, if we want to add two given series, then they must be convergent. And it makes sense because if we want to add two series and they are divergent, then it doesn't make any sense because if both series or one of the series is divergent, then adding them won't give us any useful information because it is going to be most probably it is going to be divergent, and that will not give us any information about the addition and the more structure about the series. So that's why in this discussion we are going to impose the condition that the series are convergent series. Now let's begin with the recall of series or infinite series. So it is a formal expression. We are adding infinitely many complex numbers z1, z2, z3 up to so on, and these are known as the terms of the series. Now let's begin with our first definition where we want to add two convergent series. Okay, so Zn and Wn, and their sum is defined in a very simple way, Zn plus Wn. So the first term will be obtained when we put n is equal to 1. So the first term is Z1 plus W1. So the second term is Z2 plus W2. The third term is Z3 plus W3. So of course we can guess that we are adding the first terms, the corresponding terms of these series. Okay, so first term with the first term, second term with the second term, up to so on. Of course, you can interpret this addition in some other way as well, but this is the useful way of interpreting this addition of two series. Now let's see some examples. We have one series 1 over n square plus iota minus 1 raised to power n over n, and we have seen in our previous discussion that this series is convergent. And the next series is 1 over n square plus iota over n cube. And using our previous discussion or using the relation between this complex series and its corresponding two real series, it can be checked that this series is convergent. And I'm leaving this as an exercise for you to check that this series is convergent. Now, given two convergent series, we want to add them now. Okay, so the addition is here. Now, according to our previous definition, the addition is going to be defined in the following way. So we are adding the corresponding real parts and the imaginary parts separately. So in other words, we are adding terms with the corresponding terms. So the sum of the series is going to be in a very simple way, 1 over n square plus 1 over n square, or 2 multiplied by 2 over n square plus iota minus 1 raised to power n over n plus 1 over n cube. Okay, so it's an exercise for you to check whether this new sum, which is a new series obtained from adding these two convergent series, to check whether this sum is convergent or divergent. Okay, and why it is convergent and why it is divergent if the answer is divergent. Now let's go on to our next very simple operation on the series. If a series is convergent Zn and we are given a scalar, then how to multiply this scalar with the series. And the definition is very simple. We add each and every term with this given scalar c. So in other words, the sum is going this multiplication, the scalar multiplication is going to be equal to the new series where the terms are c, z, n. Okay, so that's how we multiply a given complex number with a convergent series. So let's see some examples. So once again, we need to consider a convergent series 1 over n square plus iota minus 1 raised to power n over n, and the complex number that we consider is 3 plus iota. Now we want to multiply this complex number with this series. Now let's see how to do that. So according to the definition, so this is going to be equal to C multiplied by this series, and by our definition, this is going to be equal to 3 plus iota multiplied by the terms of the series. So each and every term will be multiplied with this complex number 3 plus iota. And of course, so one simple observation is that this C must be constant. So if this C depends on, for example, n, then we cannot move C inside or outside this summation. So it has to be a constant, a fixed complex number with respect to, of course, this index n. And if we multiply these two complex number 3 plus iota and 1 over n square plus iota minus 1 raised to power n over n, then using simple complex number multiplication, this is going to be equal to this new complex number. So that's our new series, which is basically the multiplication of this given infinite series with the complex number C. Now let's begin with this product of series, and which is the Cauchy's product of the series. Once again, we are given two convergent series, so convergence is important here, and we want to multiply them. Then their Cauchy's product is a new series Cn, and the terms of the series are defined in the following way. So Cn is basically k is equal to 0 to n zk multiplied by wn minus k. Now it seems very complex here that this new Cauchy's product Cn is very complex, but we will see in our next discussion that this is very natural and very simple way of defining the product of two series. Now here we can see that if we consider if we take n is equal to 0, then it is going to be C0, and C0 is going to be equal to k is equal to 0 to 0, and the terms of the series are going to be, there's only going to be one term, Z0 and W0. Okay, so and similarly up to so on. Now let's explore further. Now as we have discussed, when n is equal to 0, then C0 is Z0 W0. Now if n is equal to 1, then it is going to be k is equal to 0 to 1, and so there are going to be two terms. So the first term corresponding to k is equal to 0, and the second term corresponding to k is equal to 1. And when we put k is equal to 0, it is going to give me Z0 W1, plus when n is equal when k is equal to 1, then it is going to give me Z1 and W1 minus 1, which is W0. Now what do we observe from these two terms? So C0 contains Z0 W0. So when we add two indices 0 plus 0, then it is going to give me 0. So C0 consists of terms such that when we add their indices, then it is going to give me 0. And if we observe C1, then it is going to give me 1 when we add the indices in each and every term. So the first term is Z0 W1, so 0 plus 1 is 1, and the second term is Z1 W0, and 1 plus 0 is 1 again. Now let's see if this rule is also applied to calculate C2. Now C2 is going to be equal to this expression, which we can obtain by taking n is equal to 2 in the expression for Cn. So there are going to be three terms. So the first term corresponding to k is equal to 0, second term corresponding to k is equal to 1, and the third term corresponding to k is equal to 2. So when we put k is equal to 0, it is going to give me Z0 W2. When we put k is equal to 1, it is going to give me Z1 W2 minus 1, which is W1. And when we put k is equal to 2, it is going to give me Z2 and W2 minus 2, which is W0. So these are the three terms of that defines, when we add them, it will give me C2. Now once again, the rule is the same. When we add the indices in each and every term in C2, then it is going to give me 2. So similarly, in general, we can define Cn, so which is going to be equal to Z0 Wn plus Z1 Wn minus 1 up to so on Zn W0. Now we can also see a pattern here. So as we move on, the indices of Z are increasing one by one, and on the same side, the indices of W are decreasing one by one in each term, and so that the sum of their indices is going to be fixed, which is n in this case. Okay, so that's one observation which helps us in understanding this Cn. Now let's move on to see why it is natural to define Cauchy's product in this way. To explore this thing, let's consider two series Zn and where n varies from 0 to infinity. So the terms of the series are going to be Z0 plus Z1 plus Z2 plus Z3 up to so on. And similarly, let's consider another series Wn, n is equal to 0 to infinity, W0 plus W1 plus W2 up to so on. Okay. Now, the Cauchy's product, we have defined it, and we have seen that it is Cn, and Cn is defined in some particular way. Now, let's see why this is natural to define Cauchy's product in this way. Now, the first term of the Cauchy's product is, we have seen it, is Z0, W0, so which is obtained by multiplying Z0 and W0. So once again, the rule is the same. Write down all the terms such that the sum of the indices is 0. And for the next term, we are going to apply the same rule. So the next term is going to be equal to sum of all terms such that in each term the sum of the indices is 1. So which means Z0 W1 plus W0 Z1. Plus the next term is going to be corresponding to the value 2. So in other words, we are going to write down all the terms such that the sum of the indices is going to be equal to 2. So these are all the terms such that the sum of the indices, and of course these are very special terms. So the first entry Z0 is from the first series, the second entry is from the second series. So all of these terms are such that the sum of the indices is 1. So there are only 3 terms, Z0 W2 plus Z1 W1 plus Z2 W0, and up to so on. For the next term, we are going to write down the terms such that the sum of the indices is 3. Okay, so that's what we have observed it. Now, if we are given this Cauchy's product, okay, then the point is, if the two series are convergent, doesn't guarantee that their Cauchy's product is also going to be convergent. And if the Cauchy's product is convergent, then we say that this Cauchy's product Cn is equal to the product of this series. So then we use the equality here. Now, if there is equality, then it is going to be equal to the product of these two series. So in other words, Z0 plus Z1 plus Z2 up to so on, multiplied with W0 plus W1 plus W2 plus W3 up to so on. Now, this particular calculation is going to motivate us that why we define Cauchy's product in this particular way. Now, it is exactly the same as we multiplied any two terms, for example, polynomials. So multiplying the corresponding terms. Okay, so in this way we can see that, so when we multiply Z0 with W0, then we get the first term, and then we to write down the second term, it is Z1 W0 plus W1 Z0. So, and as we have discussed it, the term such that the sum of the indices is 1, and up to so on. So in this calculation, we can see why the Cauchy's product is natural way of defining the product of two series. Now in this discussion, we have defined the sum of two convergent series, scalar multiplication of a series, and Cauchy's product of two series. Now in our further discussions, we will explore further about series and of course their convergences, divergence problems, and other issues.